Muted. We got this. All right. Good morning, everyone. We're doing unit testing today, and let's dive right into it. I don't really have announcements. I guess I'll give my quick reminder. This is the first lecture that has a programming test associated with it, which is true for all of the rest of the lectures all semester.
Good morning, everyone.
Whoa. Which is true for all of the rest of the lectures for the semester. The only, I guess, kind of exception is the last one, which is the final exam. So I'm not going to assign a homework after the last lecture. That'd be kind of silly. Though we kind of can, because we do lose the last lecture because it's July 4th. But no, I'm not going to do that. So the next 8 lectures all have a programming test associated with it. And this is where the course kind of shifts into warp speed. This is going to be extremely fast. This programming task 1, I just checked, about half of you have already completed it, so that's great, and a bunch of you already completed task 2. So we're looking good. Some of you are getting ahead on this stuff, and I do strongly encourage that. That's why I went over unit testing very quickly at the end of last Thursday's lecture, so you can have that option to get a little bit ahead. But at this point, it's hard to get ahead now if you haven't finished program task 1. The half of you who haven't finished it, get on that, get it done before that expected deadline, which is in 2 days. About 48 hours from now is when that expected deadline is. If you're not hitting this expected deadline for task 1, in my opinion, you're at risk of failing the course already. Make sure you hit that task 1 deadline. Task 1 is, can I say by far? I don't know. Task 2 is pretty easy too, but task 1 is at least one of the easiest. It's in the top 3 easiest tasks. If you can't meet the expected deadline on task 1, and you're already falling behind this week, I don't see a future where you're finishing 6, 7, and 8. These ones are all fairly tough. I don't see a future where you're finishing those on time. If you're already letting yourself slip on week 2 of the semester. So hopefully you've already reviewed all your Java basics. You're comfortable with programming in Java. You can write anything you could write in 115. Any 115 assignment, you should be able to do those in Java right now. If that doesn't describe you, you gotta be studying. You gotta be putting in those hours. But with all that, let's get into it. I already introduced Program Task 1 last time. Not going to do that. And I won't introduce every homework anyway, so I don't know why I'm saying that. But let's get into this. That's my intro. Let's do some unit testing. All right, I just want to open this. Yeah. Okay. P. Hey, I'm learning my keyboard shortcuts. Okay. Oh, that was too big of a step. All right. So the big question we want to ask with testing is, how do you know your code is correct? This is a big question that will follow you throughout your career, assuming you're going into programming and software engineering. How do you know that your code is correct? And a lot of developers are going to have different answers for this. Throughout your career, you're going to have to decide how you want to answer this question. How do you know your code is correct? But I'll give you some framework of how to at least approach this question today. And over your career, you'll formulate your own opinion. This is one of those questions where if you ask 20 developers how to answer this question, you're going to get 20 different answers. So there's no one correct way to answer this, but we're going to at least talk about a few ways that are bad. Is that fair? I don't know. Main method ain't too bad. Might be some people's answer. And it's not terrible. But step 1, I see this as a kind of progression that any developer will go through, or specifically students in this case. Any student will go through as you're initially learning programming. First, your first stage of how do I know my code's correct? Well, I submitted to Autolab and I got credit. That's fine. That gets you through 115 for sure. If that's the only testing you're doing in 115, I would never recommend that to a 115 student, but you'd get through the course. Like, you would survive. 116, I do see students doing that through 116 too, and they don't really survive. That's a lot tougher to do. But submitting to Autolab, if it says you're good, you're good. It is fairly definitive. I mean, there are usually some holes in the autograder. We're not doing 100% comprehensive testing, so you could have bugs and still get through Autolab in some cases. Just no major bugs. But the more to the point, this doesn't exist out there in the real world. When you get it out there and you get a job, there won't be Autolab. There will not be a senior developer who's going to run through all of your code and check it to see if it's right. And actually, maybe some cases that might be the point. In some places that might be the case. But they certainly won't build all of this tooling for Autolab. Like, it takes a lot of work to build an Autolab grader. If a senior dev at your workplace is going to go through the trouble to do that, they would have just completed your task for you. They wouldn't have hired you. They wouldn't have assigned it to you. Like, you wouldn't be there if your senior devs were going to build something like Autolab. That's just not going to exist. That's the reality of it. That won't exist for you. So the next step of the progression is call your methods. Just call your methods and print the values to the screen. Now, this isn't terrible. You write a quick main method and call the method that you're writing, print the value to the screen, and check if the value is what you expect. The good old-fashioned print line debugging. Now, this does still have its place. You'll still use this from time to time throughout your whole career, or fairly often even. It's not terrible. It's something. Given that Autolab won't exist, it's something. It's the pretty much bare minimum of testing that you can do. But especially if there's just a really quick thing. I've talked to pretty experienced developers who said no amount of testing is a good replacement for a well-placed print line, which, fine, it has its place. But if that's your sole method of testing, I would argue that you're doing it wrong. That can't be the only way that you're testing. If it is, you're probably spending more time testing and debugging your code than you really have to. And the next progression is the one that we want to talk about in 116 that will be pervasive throughout the semester. You're either going to love unit testing and embrace it and say how wonderful it is, or you're going to hate it. Most students hate it. It's just the reality of it. But it's one of them kind of necessary evils in programming. No dev likes to write their unit tests, but man, are they useful. They're helpful, and you're going to have a lot fewer bugs when you release your code if you have proper unit testing, which, like, you've used software before. I'm sure you've used software with bugs. Like, bugs exist all over the place. That is, in my opinion, I'll qualify this with in my opinion, a symptom of developers not wanting to write their tests. It's kind of like our eat your vegetables type of thing. But, man, is it powerful, it's helpful, it's going to reduce those number of bugs that make it into production and make it to the end user. And I'm sick of using buggy software, personally. I wish more devs would do their testing. But let's talk about what this is. That's what we're here for today. What unit testing is automating the process of testing. So we're going to write some code that tests our code. So we're going to write code that automates the input-output behavior of the methods that we want to test. And as long as our code that we're testing is correct on every single input that we give it, it always gives us a correct output. Then we're going to say that it passes our tests. And with unit testing, we do demand perfection. This will be a theme throughout unit testing. We do demand perfection, in that if a method fails a single test case, we say that that method is wrong. We can't say, okay, this method's right on 99 inputs, but on the 100th one, it didn't get that one right. We're not going to say, yep, ship it. That's right. That's good for users, because guess what? 1% of the time when people are using our app, it's going to be a bug. I mean, roughly, depending on what the inputs are and everything. that we don't want that. We can't accept that. We know there's a bug. If we failed our unit test, we know there's a bug. We know there's a case where our method is wrong. We have to fix that bug. We do demand perfection as developers. Unit testing reflects that. It's going to demand perfection. We have to pass all of the inputs, every single one. The mic just got really loud. Let me tone that down. I don't know why this. I feel like this mic just changes its behavior. Let's see, a little more than that. I feel like this mic just changes its settings randomly. I don't know. It's annoying. How are we? Does it at least sound better? Like just got bass boosted. Like I didn't touch anything. It's really annoying. Settings randomly. I don't know. It's annoying. How are we? Does it at least sound better? And it has that crappy. Got my gain all the way down. Got the right pattern. This thing's so annoying. And it does sound kind of crappy too. I have no filters. Maybe I should add a filter? I ain't gonna mess with that right now. Let me just tone it down a bit more. Alright, hopefully that's at least better. I might just be louder today. I feel like I'm talking a bit louder too. I'm just excited about unit testing. But it was good at the beginning of the stream. All of the rest of the lectures for the from now is yeah. But if that of the input. It might just be louder today. No, it's just sucky. It was fine at the beginning of the stream, and then it started sucking. When you turn your head, it gets better. But I didn't move the mic. Like, I didn't change anything. That's what frustrates the hell out of me. Like, nothing changed, and it was a very clear point in the stream where it just started sucking. You know what? I'm going to try to change the pattern. I don't like doing that, but let's see. Okay, let's give this a try. But it was good. You know what? I'm going to try to change the pattern. I don't like doing that, but let's see. Okay, let's give this a try. You know what? I'm going to try to change the pattern. I'm just gonna. Oh, son of a bitch. Really? All right. If this doesn't do it, I just got to keep going with lecture. But I think I have high hopes for this. I have high hopes. Oh, my face isn't there anymore. All right. Hey. If this doesn't do it, I just got to keep going with lecture. There we go. Okay. I think I have identified and solved the problem. Woo. And tea down. Okay. Now we're ready to freaking rock. I should have thought of this earlier. I forgot that I still had this, actually. But I have this USB hub that's been giving me issues the whole time. So I had the mic plugged into that. I thought I already had it plugged into my desktop directly. So I corrected that. And I think it's the hub that is the issue. So I'm going to throw this hub in the garbage once I figure out what else is connected to it. I think my mouse and keyboard are. And be done with that. So all that time I was blaming the mic. Sorry, Blue Yeti. My mic is fine. It's the hub, though. That hub's absolute garbage. I had my capture card plugged into the hub before, too, and it caused every issue imaginable. It's just sucks. Okay, so our test needs to be correct on all inputs. So what do we mean by unit tests? Let's kind of go through our testing progression and test this admittedly very simple method where we're adding 5 to the input. We're going to take an int, add 5 to it, and return that int plus 5. That's it. That's all we're doing. A method that you would never actually write. There's no reason for this to exist. You would just add 5 in line without calling a method. At least a method with the purpose of adding 5 shouldn't ever exist. Just use the add method. But this gives us a very simple method where we all know what the expected inputs and outputs are going to be. We don't have to focus on the code of the method itself because I want the focus of today's lecture to be on testing. We want to focus on how to test something, not what we're testing. So let's test this and make sure it's correct. First thing we would do is write a main method. This is the 115 method. And hopefully, I forgot to mention that. Hopefully by the end of 115, you all got to this point where you were at least calling your own code. This is one of the struggles in 115 that the TAs and instructors have to have with you. Have not necessarily with you, but with the whole class in office hours is a student will come to office hours and say, Autolab said my code's crappy. And we'll say, well, what do you think about your code? What does it do? And the student will be like, and then you say, well, can you at least call your method and see what it returns on a couple of inputs? And it's a struggle, but we usually get everybody to this point by the end of the semester, where you're at least calling your own code, printing it the values that it returns to the screen, and then manually verifying with your eyeballs that it printed out the right thing. So this is our part of our progression in the first point where you're actually testing your own code to some degree. So here we're calling add 5 with 2, 5, 1. As long as we get 7, 10, 6, we're happy. But we do have to look at this with our human eyeballs, what's printed to the screen to verify that it is correct. And in this case, with these 3 inputs, this isn't too bad. I mean, it's a little bit of work, but whatever, we'll live. We can check these 3 numbers. But what happens when the code gets more complex? Like, this is 3 test cases with the add 5 method. Even here, once we have like 20 test cases, this is going to get tedious. And what happens when we have more complicated methods? We have a method that's going to sort any number of songs by title and artist. And we're printing out hundreds of inputs to make sure that we're always getting the correct sorted order. And we're sifting through all of these songs and trying to figure out if it is in fact the right order. We're singing the alphabet 100 times, trying to figure out, wait, R and S, which one comes first? What was that again? And we're going to be there for a long time checking this code because we're just printing the output to the screen. So we want to automate this. That's our goal. That's what unit testing is to automate this process. So we're getting our eyeballs out of the equation and having the computer test the expected outputs for us. So with our testing, we don't just want to call this on 2, 5, and 1, print the values to the screen and manually verify. We want to automate that verification and have the testing check. Did it return 7, 10, and 6? If it did, then we're good. If it didn't, then we're bad. That's what we want, and this is how we're going to build our unit test. This is what we're going to build our unit testing to do. Okay, so the structure of a unit test. I did this very briefly in the last lecture, but just to get ahead of, just to get you started on homework 1, task 1. If I say homework, I mean task. By the way, I call them tasks in this class, but sometimes I'll slip. I'll call them homeworks, projects. There's only the programming tasks. That's the only homework assignment. And then the quizzes, that's the only assessment. So if I say exam, midterm, final, quiz, trace, memory diagram, I mean the same thing. If I say task, homework, project, I mean the same thing. I've had a lot of students in the past say, hey, you're talking about projects and homeworks in lecture, but I only see tasks on the syllabus. I slip sometimes. I use them interchangeably. I'll try to stick with tasks, but if I do slip, I do mean programming task. So with that disclaimer, let's get into the structure of a unit test. This is an external library. This is our first and only, I think this is the only external library. Yeah, this is our only external library we use in 116 right now. It might change in the fall. I'm looking to change things up. But this is our only external library, meaning that the JUnit library that we're going to use does not come with Java. It's not packaged with Java at all. So this needs to be installed separately. It needs to be linked to your project. This is something that can be quite a process. It's quite a pain sometimes. In our cases today, right now in 116, not difficult at all. If you clone the project repo, if you clone that repo, it comes with a pom.xml file. And IntelliJ is going to see that file, and it should install and download and link JUnit to your project automatically. This whole process should be completely behind the scenes to where you won't even have to think about it at all. But if you do get errors on these imports where you're importing from JUnit, that means something went wrong with your pom.xml or the Maven. I don't even have the word Maven on screen. That's how much we don't have to talk about. This used to be like half a lecture. I'd have to talk about how to install dependencies and link them to your project. With modern tooling, IntelliJ specifically, in this case, it's a non-issue. So if something does happen here, if you do get errors here, it's something with your pom.xml. Maven is the software that reads the pom.xml and downloads those dependencies. So something went wrong there. Usually when that's the case, it's because a student cut and paste the code from GitHub into a new project in IntelliJ, and they didn't clone the repo with Git. So if that describes you and you have errors here, also cut and paste that pom.xml, and then right click on the pom.xml and select add as Maven project, and that should get rid of your issues. Or use Git properly, ideally, but okay, so once we have the project installed, which should be automatic, we can import from the JUnit library. And I have one kind of different thing here, a static import. This is when we want to import one static method from a class. So the org.junit, the package, has an assert class, and the assert class has a static method called assert true. So when we do import static, we're saying I would like to import one static member of the assert class, in this case the assert true method, and then we can call assert true as though we just have direct access to that method, but it actually is part of the assert class. So we could do the same thing like we've done before. We could do import org.junit.assert without the static and without the assert true. But then every time we call assert true, we would have to do assert.assert true, assert.assert true, assert.assert true. which is fine if you want to do it that way. Whatever, do whatever works best for you. But a static import avoids having to do assert dot every time here. And for what it's worth, in this specific example, the adder class is in the same package as the add test class, so I don't have to import adder. But in your problem set for task 1, the tests and the code are in different packages, so you will have to import problem set and then do problem set dot sum of digits, problem set dot average, etc. Or if you prefer, you could do a static import static ratings dot problem set dot sum of digits, and then just sum of digits, the same way we're doing with assert true. So a few different flavors, a few different ways of approaching things. For what it's worth, I like to static import my assert statements, but not my own classes, because that gives me a very clear way of knowing where I'm calling this method from. It's just more documentation in my code. But assert true, all my assert statements, I know they're all coming from JUnit, so I don't need the class name right there. I know it's coming from the assert class. But add 5, I might forget where that method lives, and I like having the name right there. So for what it's worth, that's what I like, but you can choose whatever styles you want. And then we're going to use this test annotation. This is what we imported here. This is why test is a different color here for what it's worth. Test is an annotation that can be used to annotate our methods, and we're going to put this annotation using the @ symbol at test to annotate this method as a test method. So we have a test class. Each test class can have multiple test methods, and each test method has multiple test cases. So we have a few layers of hierarchy here. But we're going to label this as a test method. If you don't have your test annotation, your method is not a test method. JUnit will not recognize that method as a test, and it will not run your test. So you need this test annotation. It has to be here. And we'll see by the end of this lecture why that is important. The TLDR of it is we might have some methods in our test class that are not tests. So we might write some, and we will, have some helper methods in our test class that are not themselves tests, but are called by the test. So we do have to distinguish. We do have to say, hey, JUnit, these ones are tests, these methods are tests, these methods are not tests. And we do that with the test annotation. If you don't have any test annotations in any of your methods, when you submit to Autolab, it'll give you an initialization error. So if you are seeing an initialization error, odds are you forgot your test annotations. Or what some students do, this kind of doesn't drive me too nuts, but it's a battle I'm losing. I don't know what to do about it. But some students will, a lot of you will, write your code before your tests. I recommend writing your tests first. The Autolab feedback is encouraging you to write your tests first. But some of you will write your code, not write any tests at all, and then submit to Autolab. You're going to get errors there because the first thing Autolab does is check your tests. If your tests don't exist, you're going to get the initialization error. Okay, don't forget your at test annotation. Okay, then each test method is a regular method. It has to be public. It has to have a return type of void. It has to have no parameters. And then the name of the method is going to be the name of this test. And IntelliJ will take this seriously. Autolab will take this seriously. You'll see the names of your test based on the names of the methods defining them. So when you run in IntelliJ, you'll see the feedback for each one of your tests. And in Autolab, when you submit, you're going to get feedback on each one of your tests individually as well. Specifically, where this is most useful is, actually, I guess the only time I give feedback on it anymore is when your tests are being checked against a correct solution. It'll give you the breakdown of each one of your tests by name. And if there's an issue, it'll tell you which of those tests had issues, so you know where to start your debug process. So you can have multiple tests in one class, and I do recommend that because you'll get the extra feedback in Autolab, and throughout your career, you'll just have more information, more finely grained information about when a test fails, what exactly went wrong. If you have more tests, if you have all of your tests in one giant testing method, and that method fails, you just don't get much information. But if I have this broken into multiple methods, it's going to give me more information about what went wrong, what I need to debug, what I need to fix when something does go wrong. And finally, we're ready to write our test cases. So we want to write our test cases. For this, we're going to use the assert true method for now. Assert true is the test method. This is how we tell JUnit that we're checking something. We want JUnit to check this. We want to say assert that this is true, meaning check to see if this Boolean expression resolves to true. And if it does, we give this some Boolean expression. If this resolves to true, then this test case passes. If they all resolve to true in this case, then this test method passes. This is the only test method in the test class. That means the whole test class passes. If any one of these asserts fails, then the test itself fails and the future test methods, test cases don't execute. So say I write this method in a way where it's correct on input of 2, but it's incorrect on 5. For some reason it returns 11. Then this Boolean expression will be false. This assert true will fail. This test case will fail. And then the test ends, and add 5 will never be called with an input of 1. That test case will never be executed. All right, I had to turn on my fan. It's surprisingly hot in here. All right, so we do demand perfection here. We need all 3 of these to pass. If any one of them fails, the code's wrong. It's just wrong. We demand perfection. I warned you, and my head does block some of this. It says entire behind my head. The test suite will demand perfection. We demand perfection as developers. We want our code to be perfect. Well, perfect is a strong term, but we need our code to be correct on every input. It needs to be correct. If there's one input that it's wrong on, it's wrong. It's just wrong. And notice that there is no main method. I said every Java program starts with a main method, but we have no main method here, but we can still run our test cases. So there's no real magic here. No, there kind of is, but not really. When you have this test suite, let me hop over to IntelliJ actually, just show it. Excuse me. I do have a planned time to do demos today, but let's get in there. Let's get in there earlier than that. Recent. We are on week 3. We're in week 2. I guess I put weeks 1 and 2 in week 1, or whatever. But when we run this, we're going to get our test methods. I have 3 test methods in this case. And we'll get feedback on each one. And when we run our tests, we're going to run it by right-clicking, either clicking up here, or what I prefer is right-clicking on the class name and run it. So I can still run this as though it had a main method, even though there is no main method in here. So this is a little mysterious. It's not strictly magic, but what's happening is, you know what, I'm going to sneak in the debugger here. If I run this in the debugger, I always like to find as much time as I can to do debugger, which usually isn't much time. But we'll get our first taste of it here. I'm going to run the debugger. That's going to pause my program and show me all of the stack frames that are on the stack. We can see that there's all kinds of stack frames on the stack right now. And the first one is a main method, which is in an IntelliJ library that's running JUnit. So when I right-click this and click Run, it is running a main method, but IntelliJ is smart enough to see this as a JUnit test class, and it knows to run its main method that runs the test runners, creates an instance of my class, and then runs my test methods. So there is a main method. It's just kind of invisible to us, and our tooling hides that in the background so we don't have to care about it. So there is a main method. We just don't write it. So our tooling, our IntelliJ, is giving us those convenient buttons to just run this as though it had a main method. It's not magical. It's not running code without a main method. There is a main method under the hood. We just don't care about it. Or, I mean, you might care about it, but we don't have to care about it. So now the big question, the how do we know if our code is correct question. Well, how do we know it's correct? We're going to write some unit tests. We're going to run those unit tests, and if our code passes on those tests, passes all our test cases, then we're going to be happy with that, right? That's kind of our answer. That is our answer right now for the entirety of 116. That's our answer is write unit tests, run those unit tests. If our code passes every test case that we threw at it, then we're good. Our code's correct. We're not going to ever be 100% sure, but we're pretty sure it's correct. If we're not that confident that it's correct, that's a good indication that we should write more tests. You should write enough tests that you're satisfied that if your code passes those tests, that the code's most likely correct on every input. But we'll never know if it's correct on every single input. That's a topic for 250 and 331. How do you know if your code's correct on every single input? Well, you're going to write a mathematical proof. For 116 purposes, we're going to throw a bunch of unit tests at it, and if it passes all our unit tests, we're going to be reasonably sure that our code is correct. So, is this enough testing? That's what our question becomes now. Is this enough testing? We have 3 test cases, 2, 5, and 1. Can we say any implementation of the add5 method that passes these 3 test cases is correct on every single int that we could possibly give it? Is this enough testing? And hopefully you will all say no. We should have one unanimous no, that's not enough testing. That this is a pretty clear answer. This is not enough testing. So we want more testing, and again, this will be a theme throughout the semester. More testing. If you come to office hours, Autolab is mad about my tests. What do I need to do? Write more tests. Write more complex tests. Write a more variety of tests. Write more tests. More tests are never going to hurt. It's never, there's not, I can't quite say that, but there's no senior dev somewhere saying, hey, this is great and all, but you did way too much testing. They might say that because of other things. Maybe you went way overboard and spent a whole week of your time and when you should have got other tests done. Things like that. But in general, it's never going to be too much testing, but you can certainly have not enough testing. There's a lot of bugs that get through because somebody slapped a couple of test cases on their method and said, yep, I did testing, check that box, and they actually didn't really do testing because they tested on 3 basic inputs like this and said, okay, we're good. So let's add some more. This is what I would call, and I'm going to break this into categories. This is what I would call the common test cases. This is like the most expected inputs that we will see. These are small positive integers that I'm going to throw in this method. This is like what our method is primarily designed to handle. This is the first thing that we're going to think of oh, add 5, you're going to add 5 to like 2 and 5 and 1. Those are the first test cases that are going to come to mind because those are the common ones. Next, we want to think of the uncommon cases. So here's an incorrect solution for this code, which is, again, the code is so simple. We're just adding 5, so I had to get a little creative on how to break this. Bugs are going to be more mysterious than this one in most cases. But here's an implementation of the method that passes these tests. But this is clearly an incorrect implementation. It doesn't handle negative numbers. So we have an incorrect solution that our tests do not identify. And your goal with unit testing is to identify any bug that could possibly occur in any implementation of a method. I see a lot of, not just students, but developers get in the trap of testing their specific implementation of a method so they know how they wrote the method, and then they tailor the test cases to the method. This isn't the way we're supposed to write tests. We should write tests for any implementation of a method. So any implementation of the add5 method, think about what could possibly go wrong. What could a developer potentially write that's incorrect? What test cases might they miss? And for our purposes here, spoilers, but positive numbers, negative numbers, and 0. Those are the 3 big cases that we want to hit, and some pretty large numbers. We want to get numbers up in triple digits and stuff. Those are the test cases that we want to test. That's what we're eventually building up to here. So you want to think of what could go wrong. Well, I know that my implementation handles every single input, so I'm going to put a few test cases on here to satisfy Autolab, submit it, and write more tests if Autolab's mad at me, and replace Autolab with your senior developer when you're on the job. And that's not the approach that we want to take. We want to say, what could go wrong with this implementation? Well, somebody might write this method that doesn't think about negative numbers, doesn't think about 0, they don't think about these things. So let's make sure our tests are going to get rid of those incorrect solutions. And one practical reason for this, by the way, this isn't just an exercise in busy work or anything. A practical scenario, something that you're going to face out there in the world, is you write this add5 method. It's beautiful. It just x plus 5, flat out, done. That's it. Easy peasy. You write a few test cases because your boss forced you to, and then your code's done. You have really weak test cases, but what's going to happen in the future is another developer is going to come on the job, and they're going to have the task of rewriting your method. They're going to say, hey, we have this add5 method. It's called a billion times throughout this project, and it's kind of slow. Can you write it more efficiently? And they're going to come up with some really convoluted, complex way of implementing the method, but it's a few nanoseconds faster. So everybody's happy with that new implementation, and they're going to run your tests because no dev's going to add to a test suite that already exists. It's hard enough getting devs to write tests. They're going to run your test suite, which is 2, 5, and 1. It's going to be correct on those 3 inputs. They're going to push it to production, and all of a sudden there are bugs. A billion places in the program, you got the wrong result for this method because they didn't handle negatives. Because they did something really silly like this. They took an absolute value somewhere. And now you have broken code. The whole project's broken. Customers are calling up, sending emails, submitting support tickets. Everything breaks because somebody re-implemented your method. So when you write your test cases, you need to be thinking of what could anyone possibly do wrong when they implement this method, and get a nice comprehensive test suite of all the inputs. Not every possible input. It's possible but impractical to do that. In this case, because we have integers, there's a finite number of integers, but your program will run forever doing your tests. But we do want a nice sampling, a nice variety of test inputs that gives us coverage of every type of input that we could throw at this. So we're definitely missing negatives, so let's get at least negatives in there. I'm going to add a second test method, and we'll get a couple of those larger inputs here, and then test our negatives. I'm going to do my negatives in another method. So when I run this test suite and I get my nice display in IntelliJ, it's going to say pass test add5, failed, test add 5 with negatives. And now I know at a glance, okay, my issue is with negative values. So now with this testing, my broken method is out of there. That re-implementation that somebody saved a few nanoseconds, my test suite is going to say, no, that's completely wrong. Like, get that out of here. But my correct implementation is still going to pass these tests. So our test should be pass on correct solutions, any correct solution. But any incorrect solution, the test should fail. The test should identify any bug that somebody could write in this method. And, there does have to be a stopping point. We're going to ask the question a few more times, when is enough? And we do have to stop at some point. So somebody could write, if x equals 1,248, return 0, else return x plus 5. And there's one very specific input where we're wrong. Like, we're not going to catch that bug. That's unreasonable to test for that. Nobody's going to get mad at your testing if somebody wrote that bug. If that bug is if x equals 0, well, you better be testing that one. That's the next thing we're going to talk about. But if it's some random specific number, like, we're not getting absolutely everything. We can't guarantee we're correct on every single input, but we should be reasonably assured that we don't have any major logical errors in our code. So that's our uncommon cases, and when you write multiple test methods, make sure you annotate each one of them with the test annotation, or else if we don't have the annotation here, that's not a test, and then we'll only get this one executed, and it was a waste of our effort to write all those test cases. So make sure you have your test annotation. And then finally, is this enough testing? Well, no. It's not enough testing. I already spoiled the edge case here, but hopefully y'all would come up with this one anyway. Next, we want to get our edge cases. So here's another incorrect solution. There's only one input that this is incorrect on, but this isn't, the example I just gave where it's some random, 1,248, not just some random number. This is an edge case. This is incorrect on exactly 0. So if x is positive, add 5. If x is negative, take the negative absolute value. No reason to actually do this, just for an example of some, there's a lot of crazy code out there, by the way. Like, some developer out there probably would write this in this way. I've seen enough student code that, some people do really weird things that you would never expect. So when you're testing, you need to be thinking not necessarily how they're going to write their silly code, but that they might write some really silly code. And you want to make sure you have test cases that are going to handle that. Not everybody's going to implement this method as return x plus 5, believe it or not. Like, people will write some really, really wacky stuff. And not just for optimization. They'll write, wacky stuff just because. And then else return x. If x is specifically 0, it's false. False, return x. We return 0 and not 5. So we want to test this edge case. Edge cases are any input where the code is going to do something different, something specific. Some cases, some inputs that need to be handled usually with extra conditions, not necessarily in this exact method, depending on how you implement it, I guess. Implementing it like this, yes, 0 takes some special code, and that's our edge case of 0. So 0 is a special case that should be handled differently. You want to make sure you have a test case for this, because somebody might implement this method in that wacky way or some other wacky way where the input 0, it just breaks on 0. A lot of times on inputs of 0, you might get a division by 0 method. If your method takes an int or a double, your edge case is almost always 0, 0.0. If your method takes a string, your edge case is almost always the empty string. If your input is a data structure, it's almost always an empty data structure. These are your edge cases. You should always have these cases. I shouldn't say always that strongly. There will always be exceptions to the always clause. But your empty data structures also. These are usually specified in the homework document. I'll say explicitly in a separate bullet point, if the input is an empty hash map, this is what you should return. So when you see those bullet points, you should be automatically thinking, oh, Jesse's giving away the edge case. Let me make sure I have a test case for that edge case. Kind of make it hard to miss these in 116. Again, you're just learning how to do unit testing, so I don't want to make it too tricky. But I do want to make sure you understand the concept of unit testing. So here we have our common cases, just regular positive integers, what we would expect. The first thing when you see this method, the test cases, the inputs that you would expect to be given. Then your uncommon cases, something that takes a little more thought, like what different kind of things are they going to throw at me? And in this case, that's our negative numbers. And then finally our edge cases, our edge case of 0 in this case. That could be a little bit different. Somebody could have different code, especially if somebody wants to get really a bit too smart on this one and use recursion to implement this method. It could be wrong on 0 if they get too fancy with it. You shouldn't use recursion here because that's slower, but somebody might do it. And if you're ever unsure, write lots of tests. If you're not sure. If you have enough testing, just write more. Just add more test cases. More test cases are going to be better. And when you write lots of test cases, because I see a lot of students go down, take a wrong turn when they hear me say write lots of test cases. They'll come to office hours. Autolab's mad at my tests. I'm not getting past the testing phase, and I say write more tests. Like it's going to be one of my common answers. The trap here is don't write a lot of test cases that are testing the same thing. Don't write similar test cases that are fairly uniform in nature. Don't get into that trap. So I'll have students, if this is an example, but basically the same thing. I'll have students where if they were testing the add5 method, they'll have the common cases, and then they'll be like, oh, Jesse said write lots of test cases. I went to office hours. He told me I need more test cases. And they'll write more common test cases. I'll see students with, again, similar, but just I'm using the example in front of my face, is they'll have 100 test cases that are all positive integers for this method. 100 test cases. And I'll say, you need more tests. They'll say, I have a freaking 100 test cases. How many do you expect me to write? This is so tedious and ridiculous. Why are you making me do this? And when I say lots of testing, that's not what I mean. I don't mean more test cases. I kind of do implicitly. But I don't mean more test cases. I mean more variety in your test cases. Variety is going to take you so much further than just strictly more test cases. So if you have a handful of positive test cases, a handful of negatives, and 0, that's perfectly good testing for this method. I might want to add a few more large numbers. I might want like a few 7-digit numbers in the millions, both positive and negative. I might add those to really round this out. If I'm having trouble testing especially, I want to test the very large values, especially in that case where somebody did use recursion. It's going to fail on the very large numbers depending on how they set it up, because they're going to get Stack Overflow errors. So I want to make sure I get those test cases in there. But lots of test cases does not mean just sheer volume of test cases. It means more variety. Each test case should be identifying a specific bug. And, I like to do overkill, so I have 5 test cases that are pretty much all testing the same bug. You could argue that 100 is testing a different bug because it's larger. And then I have at least these 3 testing the same bug, and 51 and negative 51, negative 100 are probably testing the same bug. So a little redundancy isn't going to hurt. But each test case should be identifying a specific bug. And if you're identifying the same bug with 100 test cases, it's not going to, I'm testing 1 through 100, all those inputs. That's pretty much just as effective as these 5 test cases. Even though I'm not testing every single input, those extra inputs, those other inputs that I would be getting, those other 95 inputs, are just redundant. And there's very rarely going to be an implementation that those 100 test cases find a bug that these 5 test cases would not catch. So what I mean by more test cases and lots of test cases, add more variety to your test cases. For a better example, the average method on the homework, it takes the average of an array list of doubles, returns the average. I've seen students with, 10 test cases, 15 test cases, 20 even, where every single input is an array list of 3 positive doubles. Every single one was the same size array list and no negatives. I've seen that in office hours before. I forget the exact number. I think it was like 10 test cases. Every single one was testing the same exact style of input because they just cut and paste their method 10 times and then changed the numbers. That's all they did. And they're like, why I have 10 test cases? Isn't that enough? Like, you can do testing for that method with, I think, 3 test cases would be the minimum to get through all of my checks in Autolab. But, like, those have to be 3 very different test cases. You need variety. Would the test get an error for initialization if you test for a float since your code takes an int? It wouldn't be the initialization error that I was referring to earlier, but it will give you an error of, it depends exactly what you mean by that, actually. If I put like 7.0 here, that would actually be fine. I believe that would work fine. It's bad for a reason we'll talk about later in today's lecture, but I think you would get away with that one. If you had double here, then Autolab's going to yell at you because now you didn't implement the method, because I won't be able to find a method with the right signature, with the right return type. So Autolab's going to say you didn't even implement the method at all. So it will give you an error, but it'll be a compilation error. I forget exactly what it says. I think I replaced the feedback and it just says error, reread the document or something like that. I forget exactly how I word it. But that would be bad. If this is double, then Autolab's going to be mad. But here, I think you can get away with that. If you do 2.0 here, that'll be an error as well. You wouldn't even be able to run the code in IntelliJ in that case. And as is the case here, testing will often be more involved than actually writing the code. I think this is one of the big reasons why it's hard to get devs to write tests, is sometimes it more than doubles your work. When your workload increases that much, it can be a pain. But it's way better than releasing buggy code. Because as much as devs love to think that they can just crank out any method and it's right the first time and ship it directly to the customer, it's not the case. Devs write bugs. The computer has never written a bug. Only developers write bugs. They write lots of them. And they make it into production, even in some very large pieces of software that we all use. Large as in widely used. Millions of users, and they'll release bugs. Oh yeah, I read float as double. So my answer applies whether you mean float or double. Yeah, I just assumed double when I read float. I read float as floating point value, which a double is a floating point value for what it's worth. But yeah, either way, float or double, same answer. Okay, testing in CSE116. When I'm full screen, I don't have a clock. 8:59, we're fine. The third, what is normally Friday lecture of this lecture, that sounds weird saying it like that, is a little late, so we'll be able to make up that 10 minutes, no big deal. Actually, I'm going to spend even more time on this lecture. Usually this one goes over, and then I catch up the rest of the week. So we can do that all within one lecture over the summer. So when you submit to Autolab, you're going to see 3 phases of testing. And for most of the other tasks, it's going to be 4, because we're going to have a testing utility method. The testing utility method is written like it's my test against your code. So it's written like a method where you just write the code without the test. We can talk about that when we get to task 2 when it's relevant. For task 1, there's going to be 3 phases of testing. One is running your tests against a correct solution. This is the very first thing that happens. So you're going to submit your code and your tests. That's your zip file for your submission, has your code and your tests in it. The first thing I'm going to do is ignore your code completely. Your code gets completely set aside, and I'm going to test your tests. Autolab has code that's going to test your tests. So we're multiple layers removed from writing code at that point. I had to write tests that will test your test in Autolab. So the way to do that, and the way to read, most importantly, I want to get you to the point where you can read the feedback and make sense of it. The very first thing is going to be running your tests on a correct solution. And for those of you really paying attention, I know I said this at the end of Thursday's lecture, but it's important. I want to make sure I get it in twice here. Plus, again, it presented through the slides instead of just on an offhand comment. So first, I'm going to run your tests against a correct solution. So I have my solution. I sat down and I went through task 1, wrote my code for task 1, and I put that code on Autolab. I'm going to take your tests and run your tests against my correct solution. And your test should say my correct solution. I promise you it's correct. It does the right thing. It will return correct outputs for every input. And if your tests say, no, that's not a correct solution, then there's something wrong with your tests. So you need to go through your tests and figure out why your test rejected a correct solution, a solution that does return a correct output for every input. You have to figure out what's going wrong with your test. For task 1, for the first 2 methods, for average and sum of digits, that one's pretty straightforward. You just flat out have a broken test case because there's only one correct solution. But when we get to best key, that's where this is going to be more relevant. This is where we're going to see more office hour questions about this, more Piazza posts about this. With best key, when there are multiple correct solutions, with the cat dog example in the handout, when it's that situation, what a lot of students like to do is say, well, my code returns cat, so I'm going to assert that the method returned cat on this input. But that's not a good test case. It's a bad test case. Because what happens when you submit to Autolab and your test is ran against my solution, my correct solution returns dog, which is a correct solution. It's a correct return value. But your test is saying, well, that ain't cat. Fail. That's not the way to write tests. And it's set up like that way on purpose. Specifically, task 1, that best of key is designed to extract this exact situation, this exact scenario where there are multiple correct solutions, and your test needs to accept any correct solution. Even if your code always returns one specific solution, your test needs to be coded in a way that it will accept any correct solution. So you need to write your tests in a way that will accept any correct solution, and I'll make sure. I won't make sure. What am I saying there? I'll make sure that you are passing my correct solution. So that's what the correct solution is doing. In most cases, so in summary, in most cases it's just checking if your test cases are broken. Oh, actually, I do have another point that I want to make here that I always make somewhere. Right here is good a time as any. Usually I'm rushing this at the end of a lecture, so I don't get to make the point here. Anyway, so your tests, usually, in most cases, it's just making sure your test cases aren't completely ass broken. But when there's multiple correct solutions, and we'll get into this even further in a later, I think task 6, it comes back in a major way, is when you're testing a data structure where the order doesn't matter. So my correct solution can return any possible order of the correct values, and your test needs to mark that as correct if all the right values are there in any order. So you can't just say, here's my my expected value is this array list with these values, and then go through the array list and make sure the array list have all the same values in the same order. You have to take that order into account, which adds a little more complexity to it to be able to make sure you're accepting every correct output. So the point I want to make right now is with broken test cases. Some students will just have flat out broken test cases. Like you're just testing completely the wrong thing. And in most cases, what happens, how a student gets broken test cases, because you really shouldn't have broken test cases. You should read the homework document, write your test first, work through without your code, work through on pen, paper, calculator, however, work through correct input-output pairings, and then write those test cases without using your code, without having the code. The code shouldn't exist yet, so you can't use your code to generate those test cases, and that's my point. Do not use your code to generate your test cases, because this is what students will do if they have broken test cases that are testing the wrong thing, is they'll read the homework document, they'll ignore my advice to write the test first, they'll ignore the Autolab structure, the feedback and everything, and they'll just jump right to phase 3 of testing, phase 3 of the homework, and write their code first. This will probably describe a lot of you. If this is your approach, as long as you're right, I'll never know. It's when if you're wrong and you're coming to me in office hours, that's when I'm like, come on, man, like I told you not to do this. And now you're facing the exact situation that I was trying to prevent you from falling into. You write your code first. You're a God developer, so you know your code's 100% correct. You just cranked it out and said, it's good. And then you write your test inputs for your test cases, call your code, get the outputs, and then put those outputs as the expected outputs. Don't do this. I'm warning you, don't do this. If you do this and you have issues, you only have yourself to blame here. Because what you're doing is using your code to generate your test cases. Do not do this. Don't use your code to generate your tests. Because what happens in this situation is you have a bug in your code because you're not actually a God programmer. You have a bug in your code, and now you generate your test cases with buggy code. Now your test cases are specifically designed by your code that the test cases are supposed to be testing, which means your tests aren't testing anything at all. You're testing your code with test cases that were generated by your code. Like your tests, you can't be wrong, right? Your test cases will always pass in IntelliJ because you used your own code to generate your test cases. But if your code's buggy, now your code's wrong and your tests are wrong. You submit to Autolab, your tests get rejected, and then you say, well, it passes in IntelliJ, and I'll always say the same thing, like, well, your code's probably wrong then, because did you generate your tests with your code? Yeah. Did I tell you not to do that in lecture? Yeah. Did you do it anyway? Yeah. And do you have the exact situation that I told you you'd be in if you did that? Yeah. It's an awkward office hour visit. Don't use your code to generate your test cases. You should generate your test cases by hand or some external tools. When the data gets big and there's big data structures, I like to go to Excel or Google Sheets these days. I'll go to a spreadsheet and use that to generate my tests, my expected outputs. But I'll use some external tool, something other than the code that I'm testing to generate my test cases. Now for me to have the same situation, the same issue, I have to make the same exact mistake in my code as I made when I generated my test cases, which is much less likely than making a mistake once. I have to make the same exact mistake twice, which, still happens, but much, much, much more rare to be able to make the same exact mistake twice. If I make the same mistake twice like that, I probably have a misunderstanding of what's supposed to happen, what my method's supposed to be doing. So don't use your code to generate your test cases. That's my warning for that. Some of you will still do it. Again, if you are a God programmer and you're just right all the time, I'm never going to know because you're just going to get credit in Autolab and I won't see you in office hours. But if you're ever doing that and your tests are not getting through Autolab, just rethink what you're doing, please. And then the next phase, so that's phase 1, against the correct solution, make sure your test cases are correct, that they're not rejecting a correct solution. If they're rejecting a correct solution, your test cases are just broken. You need to fix that before doing anything else so you don't get the next phase of the output. Next phase, if you're correct on if your tests pass a correct solution, then I'm going to check your test for coverage, for feature coverage. In Autolab, it's going to say, do you have a test case for this feature? Yes or no. Do you have a test case for this feature? Yes or no. And the way that I test that is I run your test against an intentionally incorrect solution that has a bug in the feature being tested. So if the feature works on negative inputs, then a test case that tests your solution if it works on negative inputs or whatever. I'm going to have an incorrect solution like the absolute value one that we just saw with the add 5. I'm going to have an incorrect solution that intentionally is wrong on that feature. Run your test against that incorrect solution and make sure that your test fails that incorrect solution. Your test should be able to identify each one of these incorrect solutions as incorrect. If it can't, then you're not testing that feature. So in Autolab, I'm going to say you don't have a test case for this feature because I know that it didn't mark my incorrect solution that doesn't get that feature correct. You marked that as correct. You said, yep, that code looks fine. And I said, I know that code ain't fine. You didn't test that feature. So in Autolab, it'll say, make sure you have test cases for all these features. And this is where the demanding perfection does work in your favor. For each of these features to test, for each one of these incorrect solutions, to mark a solution as incorrect, you only need one test case. One test case that fails that solution. So one test case where you give it to that solution and that solution does not give you the correct answer. You demand perfection of these solutions. One single test case is all it takes to say, yep, we have testing for that feature. So you could have 100 test cases and a single one of those test cases marks that fails that incorrect solution and it passes all other 99 test cases that you have. As long as one of them fails that incorrect solution, you're good. You have coverage for that feature. We're going to call that good, at least in Autolab. Okay, and a few quick tips. Oh, and then the third phase, I don't know why I don't have it on this slide. Probably because I have so much text already on this. The slides took like 10 minutes probably. The third phase is my test against your code. So only after you get through all of this. All of this is checking your tests, which is probably the bulk of what you'll be doing for the programming test is writing your test cases themselves. Especially for task 1. The code isn't too overly difficult. It's meant to be 115 style coding. For task 2, I think it's even easier. I think the code is fairly trivial in task 2. But it does use classes and objects, so that's a new thing. But for task 2, the testing will take a little bit of time getting used to testing classes. Testing is where you're going to spend a lot of your time. So this is all testing. Once you get through the testing, then I'm going to bring in your code, bring in my tests, and run my tests against your code. And your code should pass on all of my test cases. Once you get all 3 phases, then you get a 1.0 for the assignment, and you're done with that task. But it's pretty rare to fail my tests. If your tests are good in Autolab, and you run your tests against your code in IntelliJ, and they're passing, in most cases, it's going to be trivial to get through my test. So it's not like a third phase. The third phase is actually writing the code, but very rarely will you get issues in Autolab on that third phase. You'll be able to do everything locally in IntelliJ and verify that everything's fine because Autolab already said that your tests are good, your tests pass your code, probably going to be good. That's less true as we go throughout the semester, especially when we get to task 8. Like I slowly back off on testing your tests. By task 8, I assume like there's the assumption there's a better word there I'm blanking on. But there's the assumption that you're good at writing tests by the time we get to task 8. You've already gone through it 7 times. You know how to write tests, and you shouldn't need the crutch of Autolab anymore. So I do still test your tests, but I test them much less so than on earlier ones. Like task 1, I'd be surprised if you can get through the testing, pass your test, but not pass my test. That'd be surprising to me. Task 8, that will absolutely be the case for a lot of you. I do a little bit of testing your tests, and that's it. I assume you can write good test cases, that you are doing that on your own without being forced to do it by Autolab. And then I will see a lot of office hour visits where your tests are fine in Autolab, you're passing your tests, and then not passing my tests, because my tests are going to be more strict than what I require for your test. So I do back off. It's a slow progression throughout the semester on how much I test your tests, but for the early tests, the early tasks, you're going to phase 3 is almost going to be free in Autolab. There shouldn't be surprises in phase 3. Okay, testing tips. Just a couple of 2 tips here. This is our way that we already wrote our test cases. Assert true. It's going to take a Boolean expression, and if that Boolean expression is true, passes. If it's false, it fails. There's only 2 possible outcomes here: pass or fail, true or false. There is a different way that we can write these. We can use assert equals. We will have to import this. Make sure you have your import. But we can use assert equals, and that's going to take 2 arguments and make sure that they are equivalent. So this is a lot better. It's a lot better, I guess. Then assert true if you are, in fact, checking 2 values for equality. So here we have 2 ints. We're checking them for equality. We can use assert equals and give it both of those ints. And I do have this backwards in my slide even. I always get this backwards. I'm starting to learn these days. It's taken me a long time. But the order should be assert equals what you expect and then what you actually got from the method that you're testing. And when you do that, you'll get a little more feedback if the test case fails. If the test case passes, who needs feedback? You did the right thing. Everything's fine. But when the test case fails, we want information about what went wrong. What happened? Because if a test case fails, that means you have a bug, and you want to be able to fix that bug. You need some information to go fix it. And what assert equals will do is print out, I expected this, I got this. Again, I have them backwards on the slide. And it'll give you that information so you can see what the actual output was, which can help you debug a bit faster. Assert true is just going to say assert failed. It's just going to say your test case failed. Deal with it. Assert equals gives you a little more information. So one reason to use assert equals, plus I don't know, it's a little cleaner. I like assert equals a little better. There will be times where you need to use assert true. One of those cases will be in the best key method. There's no easy way to use assert equals there. You're going to want to use assert true for that one. So assert true is your sledgehammer. Assert true is always going to do what you want, no matter how complex or creative your tests are set up. Assert true is always going to work for you. Any Boolean, any way that you can transform what you're doing into a Boolean expression, it's going to be fine. Assert equals, for specifically equality, can be more helpful. And then the last tip is your hint text. If you add an extra argument, it has to be your first argument and it has to be a string, then this is going to be printed to the screen if the test case fails. This can be the first argument in assert true or assert equals or whatever other assert. There's assert null, assert not null, a lot of different asserts that you have access to. Any one of them can take a string as its first argument and then whatever other arguments are expected. And it'll print this string if the test case fails. This can be helpful for pretty simple test cases to print out what the input was. So assert equals is not going to tell you what the input was. It'll tell you expected output and actual output, but it won't tell you what the input is. So getting your input in the hint text can often be helpful. It can often cut down your debugging time by a decent amount. Nothing too significant, but it can cut your debugging time down a little bit. Okay, and that's unit testing. This is the intro to unit testing. The next 2 sections of this lecture are going to be talking about implications of that. But if there are any questions while I'm switching over to the next segment. I was going to say now is the time to ask, but it's always time to ask questions. You can ask questions whenever you want. It's always question time. Okay. So I want to talk about, or somewhere in here. Is it just these ones? Yeah. So I have some test cases here. I have these two. Let me make absolutely sure I got the right ones. I want to match the slides just for aesthetics. It's hello, goodbye, and then the 0.3 one. I gotta find my... Oh, I know why, because I haven't pulled. There's gonna be all kinds of changes. Skip. I want to board and roll back. Because I haven't pulled in forever. Oh no, I fucked it up. No, because yeah, I see. I see. I'm gonna, just so this matches, sometimes Maven throws a fit, sometimes it doesn't, but just so it matches my JDK, I'm gonna change this. That's why my numbering was off. Hey, there's all my stuff. Hey, okay. So I have this test right here. I have string A, which is the string hello, string B, which is the string goodbye, and I'm going to combine those strings through this strings.combine_strings method. So here's the method that I'm testing. It takes two strings, A and B, and returns A plus a space plus B. So very simple. It's just like our add5 method. It's doing something very simple, so we all know, we all agree on what this method should return, and we can focus on the testing of it. So A plus space plus B. I'm going to call this method with A and B, which is hello, goodbye, and I would expect that to return hello space goodbye. So we can all agree that that is the expected output of this method. I'm going to use that in an assert true and check if those things are equal. I'm going to run just this test method. So I'm going to click this button here instead of running the entire class because I don't want to run the other two. We'll talk about those in the slides. But let's run this. I would expect this to pass. This is going to return hello, goodbye. In a while. It's got to recompile everything because I downloaded all the latest code. And it doesn't. Well, that's weird. That failed. So let's do a sanity check. And just print out what that method is returning. I should have done that as a hint text, just as an example of how to do that, but I'm not going back. Hello space goodbye. Hello space goodbye. I mean, it's the exact same thing. Well, I don't know. I'll think about that. I'll think about what happened there. And let's go over here. Maybe this one will work for us. We have this method times3. Again, just like our add5 method, it's simple. We can all agree on what the expected output is. Takes a double and returns that double times 3. I'm confident about this one. Like, we got this. And we have this test case. It's going to call times 3 of 0.1. I'm going to even print that to the screen. So just like we did before, but I'm going to do that off the bat. And then I'm going to assert true that y equals 0.3. 0.1 times 3 should be 0.3. I think my math all checks out here. So let's run this test. This test should pass. And, oh, wait. That didn't pass either. And when I print that to the screen, I don't quite get 0.3, actually. That's weird. Well, that sucks. So neither of those pass. And that's what, by the way, that's what happens. That's what it looks like when you have a failing test case. You'll get this yellow circle with the X, and it'll say it fails. You can click on the blue text. That'll take you exactly to the assert that failed. And anything that you print into the screen, which I should have done as hint text, but too late now, I ain't going back. And if it passes, you'll get the green check marks. But these definitely failed. So this fails. Yes, those were expected to fail, of course. But this test fails. Why? Why did this test fail? It seems so simple, straightforward, and, well, we don't use equal equal to compare strings. Never, ever, ever use equal equal to compare strings. Even if, I'll give this disclaimer right now, even if Autolab is happy with you, I should update all my graders and really make sure I test this everywhere. Even if Autolab is happy with you, never use equal equal to compare strings, because sometimes you'll get away with this. If I write this test in a different way, I can get it to pass, even when it's testing the same exact thing, and sometimes it'll fail. And the short answer to that is strings are weird. So I wrote this specifically in a way where I can guarantee that it's going to fail. And that won't always be the case. So sometimes you will just use equal equal and get away with it. That doesn't mean you're right. You're definitely wrong. Never use equal equal to compare two strings. I'll give an asterisk on this in Java. In Java, never use equal equal to compare two strings. Ever, ever, ever. Just don't do it. Don't do it. Because you will get a bug eventually. Even if it doesn't catch up to you right away, it will catch up to you eventually. You're going to start getting really weird issues. I saw someone who used, they actually used not equal in task 3 to compare two strings. And then in task, I think it was 6, either 6 or 7, they had a really weird bug. None of the TAs could figure out what was going wrong with it. And it's because that error caught up to them. They did the wrong thing. Then task 3, they got through Autolab with that bug. Because, it happened to line up in a way where they got away with it, but they didn't get away with it because it wastes hours of their time on a later task trying to figure out what the hell was wrong. And it was one of the ones the TAs couldn't figure out. I had to look into it. And, I'm not surprised no one could find the issue, because the issue was way back in task 3, which was just absurd. Yes, you can use assert equals. But I want to make sure I make this point before you all start running off and just using assert equals. So you can't use equal equal to compare strings. So what do you use? Dot equals. If you use dot equals to compare strings, then you're not going to get the same issues. The short answer is strings are weird. The slightly longer answer is strings. This is one case where we do care that strings are actually objects on the heap. They are immutable. And usually two strings with the same value will point to the same string object on the heap. But in certain cases, sometimes Java won't optimize that way, and it will create two string objects with the same values, and you'll have references to the different values. And equal equal will compare the references, not the values. Dot equals will compare the values of the strings, not do these two strings refer to the same object. That's the difference between the two. I'll cap it at that because we don't want to dive down the rabbit hole of string immutability in Java. But dot equals is going to compare the values of the strings, not the references, the values of the references. So this one passes. This is fine. Everything's great. Our method does, in fact, work the way we expect it to, but we got to use dot equals to compare two strings. For your testing specifically, you can use assert equals, as was pointed out in chat. Thank you. Assert equals, you can use assert equals. And again, I have my inputs backwards still. When I made these slides, I was backwards. Sometimes I'm backwards on this, sometimes I'm forwards, but it should be the reversed inputs. It doesn't break the test case, but if this test case fails, it will give you the wrong output. It'll say expected this, but actually got this. So it messes with the formatting of the hint text that the assert equals method gives you, is the reason to get the inputs in the right order. What assert equals does is it will take both of these values and call dot equals. Actually, let's go to IntelliJ and see that. So here's the good example. If we're on the better example, assert equals, if we run this, and here's the correct order. My expected is hello, goodbye. My actual is this. And if I go into the assert equals method, assert equals calls assert equals with null hint text, for what it's worth. And then somewhere in here, fail not equals if it's of string, it's of string. Why did I get so lost already? Assert equals, oh, because it's in the conditional. Equals regarding null. Check, make sure they're not null, then check is equals. And after we go down the rabbit hole, quite a few steps, we get expected dot equals actual. So aside of null checks and type checking, assert equals is just calling dot equals. That's what it does do. Underneath the hood, it's what its purpose is to call dot equals. So we can call dot equals ourselves, or let assert equals call dot equals. Assert equals does give us better feedback, but sometimes you do have to call dot equals. Specifically, if it's in a conditional in your code, you want to say if these two strings are correct, run this code, else run this code. If that's the case, you don't have access to assert equals there. Outside of your test suite, you don't have access to these asserts. So you do need to understand, that's why I like showing the dot equals example too. You will need that sometimes in your actual code. You're not only comparing two strings for equality in your test. So if you only know assert equals, you're going to panic when you have to write that if statement that checks two strings for equality. Okay. So assert equals, I'm fine if this is the way you always write your test cases. But you got to know that all it does is call dot equals. You need to know that dot equals exists because sometimes you will need to call dot equals. Even in your testing, in task 1, you're testing for best key. Even then, you can't use assert equals when there are multiple correct solutions. So you need to know that dot equals exists. But once you know that exists, go ahead and knock yourself out with assert equals. I always prefer assert equals over assert true with a Boolean expression, but you need to know how to write that Boolean expression and understand what assert equals is actually doing for you. It's just calling dot equals. Okay, and now let's revisit our letter grade example to give pluses and minuses. We're going to give a plus and minus based on the ones digit of your letter grade. So we're going to take our score modulo 10. Remember, let's refresh what we were doing before. We're going to take our score, integer divided by 10, to look at just the tens digit. If that's a 9, you have an A. If it's an 8, a B, etc. And I got rid of my extra stuff in the 7 because we don't need it for this one. That's not the point that we're making right now. And then plus minus is going to take the same score and decide what modifier we should give, plus, minus, or none. So we're going to take the score modulo 10. That gives us just the ones digit. And if the ones digit is greater than or equal to 7, we get a plus. If it's greater than 2 but less than 7, we're going to give it no modifier. And else, if it's 0 or 1, we're going to give it a minus modifier. And we have our main method test cases here. We expect this to be an A C plus, and an F, which is going to be one of our bugs here. Just a foreshadow. I'm not going to do the surprise again, like, oh my goodness, it failed. This is going to give us an F-, which is not a valid grade. So this is going to expose a bug in the way that we have our code here. So this code, and I'll say it right now actually, there's a few bugs in this code. This is code that doesn't work well, and we want to write test cases to expose those bugs so we can fix those bugs. That's our goal with testing. If all of our code was always absolutely 100% correct, we wouldn't write any tests. What would be the point? We would never write tests if we always know that our code's correct. It's when we have code with bugs, that's when we'll need our tests. And devs write bugs. We all write bugs. It's how we handle those bugs after we write them. That's what makes a good developer into a great developer. If you can write bugs and eradicate them before anybody else sees them, you get the illusion that you're a god developer. But really, you're just good at practicing your unit testing. Okay, so we code those up in test cases. We have, inside of the main method, we'll extract this out. And I'm going to use my hint text just to give an example of that. I'll be honest, I usually don't write my hint text. Paul usually does, the other 116 instructor, in the spring. So I made sure I added an example where I use hint text, which he actually wrote this example for what it's worth. So plus minus of 95, that should be just an A. So the plus minus method sees a 5 in the ones digit. It's not going to give a modifier to it. I'm pointing at my code. I shouldn't be pointing at the code. I shouldn't even have the code on the screen when I introduce the tests. So my hint text, if this fails, I'm going to compare what I get from the method to nothing, again with my values backwards here. PM should be nothing, PM for plus minus. Plus minus of 95 should be nothing, so empty string. I'm going to use assert equals, so it's going to call dot equals and not equal equal on these things. And my hint text is on the input of 95. That's the big thing that I have to give for my hint text, is what the input was. Input of 95, there should be no plus or minus, but this is what we actually got, and I'll print that out. On 78, I should get plus. Same thing, give me at least the input. That gives me a little more clue as to where my bug is, at least what test case failed. I have my expected, my actual, and my input. That's all the information that I could possibly need to get started on my debug process. Then I have to figure out why on this input, when I expected this, I actually got this, or this. And then on 51, I would expect a minus. So my test case is going to check and make sure I got a minus. Even though this shouldn't really be a minus. I guess we don't make that point in this lecture. That's a later lecture where we go and revisit that. But fine. We're going to say that's an F-. That's fine. I'll just verbalize this. I'll get to fix this in the next lecture when I live code it. But 51 shouldn't be an F-. That's not the worst thing, but what happens when somebody with a 48 gets an F+ and a 51 is an F-? That's really awkward. And there are no F+ or minuses, it's just an F. So for this test case should be, at a 51, should be empty string is what I would like to do with it. Again, there is a later lecture where we cover this, but I had to cut that one for the summer, so I had to talk about it right now because we won't have time to revisit this example. Once this has a minus, that should be a failing test case. I want everything below a 60 to be empty string. So we'd have to add an extra, have this test case expect empty string. That test case is going to fail this code, and then we have to update the code to say if score less than 60, return empty string, else check the ones digit. But we're just going to say that should be an F-. I guess we're going to stick with that. Here's where I get to defend myself. Paul wrote this example. I'll blame him even though he's not here. All right, so let's add a test case here. This one is going to make the point that I want to make of writing test cases to expose your bugs. I'm going to write plus minus of 100. A 100 should be an A+ with the grading rubric that we have here. Obviously at UB we don't have A+, but this should be an A+ based on the way we have things coded for this this grading structure. So 100 should be A plus. We write this test case, we run our tests again, and we fail. On input 100, it should be plus got minus. Expected minus actual plus, which of course is backwards. Even in the feedback, like, how did I not notice this? And say, oh shit, my inputs are backwards. Let me fix that. I even did the screenshot for it. Oh, sorry, No Heart DF. I wasn't watching. That was pretty old too. Yes, you can use dot equals for doubles and booleans. Oh, wait. No, I see what you're asking here. Can we use dot equals for ints, lowercase I, lowercase d doubles, and lowercase b booleans? No, you cannot. No, you cannot. I read that as assert equals. You can use assert equals on those for your test cases, but you can't use dot equals. Primitives are not objects, so your primitive types don't have any methods associated with them. Because they're not objects, they're not associated with classes, so they don't have any methods. They are strictly just values. So there are no methods. You can't, on these primitive types, you cannot do dot anything. There's no methods associated with them. So for ints, doubles, booleans, you would... Shit, I can't even say that. For ints and booleans, you would use equal to compare them. Doubles, it's a little more complicated. That's the next big thing we're going to talk about, though. So this comparison fails, and this is where you would start to say, well, I got 3 out of the 4 tests passing. That's a 75%, right? That's a C, baby. C's get degrees. I'm good to go. No, we demand perfection, just like this poor student who should have had an A plus that we assigned an A minus. This kind of bug is going to be an instant email. As soon as I post grades, I'm going to rightfully get an email from the student saying, yo, I crushed absolutely everything. Why did you give me an A minus? What the hell is going on here? And I don't want that to happen, so I'm going to write my unit tests and make sure that I don't have that bug. But the student is going to be mad. The student demanded perfection. Our test demand perfection. We were not perfect here. This code is busted. We need to fix that. So we wrote a test case. In this case, this was an edge case. 100, our edge cases are not always 0 for ints. In this situation, 100 was one of our edge cases based on our specific situation of converting numeric grades to letter grades. 100 is an edge case there. So we failed on our edge case, and as is usually the case with edge cases, we're going to have an extra conditional. We're going to say if it's our edge case, handle it separately, else handle all the other cases a different way. So we wrote our test case, we exposed our bug. Now our job is to go eradicate that bug. We get rid of that bug to pass these tests. We're going to add our conditional. If score is specifically 100, we want that to be a plus. Handle that edge case. Now we're good to go. That student gets an A plus, pass all our tests. 4 out of 4, we're good. We could edit it to get rid of the F plus and F minus bug, but I don't know. I already made my point anyway. Maybe I'll do that when I'm live coding in the next lecture. I don't know if it's worth it to make the same point twice. Maybe it will be, and that's okay. Now that we're at the end of this example, I want to revisit this conversation I started last week, but I want to make sure this is super duper explicit. Because I don't like seeing students waste time on this one, because it's not intended to be a time waster, but you don't necessarily, not everyone necessarily remembers. I think they do cover all this stuff, but remembers their tools from 115. And if you're a transfer student, you might not have seen these things depending on where you came from. But the sum of digits method. I want to talk about sum of digits for a bit here. Sum of digits. The second method in task 1 asks you to take an int and sum up all of the digits. So if the number is 123, it's 1 plus 2 plus 3. It should also handle negative numbers, so negative 123 would be the same thing. 1 plus 2 plus 3 should be 6. That's the sum of the digits of the int. So this can be kind of tricky if you don't have the tools. So I want to say, I feel like I've said this a few times in lecture already, but we have the full example in front of our eyes right now. So let me take a second to talk it over. The modulo operator, modulo 10, and divided by 10. These are the two tools that you're intended to use to solve that. Now, some of you have creative solutions to this. You solve it some other way, that's fine. I've seen students convert the int to a string, iterate over the characters of the string, look up the ASCII values for those characters, subtract the ASCII value for 0 to get the value of that digit, and then sum them up that way and have something else to handle negative values. If you want to do something like that, that's the way you want to approach this. Knock yourself out. Go for it. I question your decisions, but if you have fun doing that, that's one thing that's perfectly fine. Which actually does sound kind of fun now that I think about it. But this is the intended solution. This is the way I would expect you to do that. I don't expect you to pull up your ASCII charts or anything. This is the way I expect you to solve that problem. The kind of way I'm guiding you with this example here is you take the value you're given and you do something to handle negatives. I'll just say it. You take the absolute value of it. Just take the absolute value, and then you can assume that the input is positive. You don't have to worry about negatives once you do that. So once you have your value, you're going to modulo 10. That's going to give you the ones digit. This line right here, exactly. Int ones equals score modulo 10, or whatever you name your variable. Modulo 10 gives you the ones digit. And you use your accumulator pattern to add that to a running total of the sum of the digits. You add your ones digit to that total, and then you divide by 10. You want this to be integer division to slide all the values over by 1. So in the example of 123 modulo 10 is going to give you 3, and you add that to your sum, your running total. So your running total is 3. And then you're going to divide that input by 10 using integer division. What this will do is remove your ones digit and slide all of the digits over to the right by 1. So then the value is 12 because you divided 123 integer division by 10. That's going to give you 12. And then you do the same thing. 12 modulo 10 is going to give you 2, the next digit. Add that to your running total. So your running total is 5. Divide by 10. That's going to give you 1. 12 divided by 10 is 1 in integer division. Modulo 10, that's going to give you 1. Add that to your running total. Your running total is 6. Divide by 10. 1 divided by 10 integer division is going to give you 0. And then you can modulo 10. 0 mod 10 is 0. Divide by 10 is 0. Modulo 10 is 0, 0, 0. And it's just going to be 0 forever at that point. So that's your structure, and figuring out, there's almost nothing left to figure out there. But I'll let you figure out the rest on your own, how to repeatedly do this. But that's the idea. And then combine that with what we've... No, I can't say the last part. I give it away way too much of this one. But I don't mean for the code to be tricky. With sum of digits, I want you to write test cases. That's what it's supposed to be about. So I don't want the code to be too convoluted. So that's why I give you such a heavy-handed hint on that one specifically. The other ones I'm not giving hints on because you should know how to do those. It's pretty much all accumulator patterns. 3 accumulator patterns with slightly different applications each time. Okay. So this test also failed. We were just multiplying by 3, and this one failed. Why did this one fail? This one seems so straightforward. It's just numbers. 0.1 times 3 should be 0.3. Why would this ever fail? And the short answer, the TLDR of it's going to be, don't use equal equal for doubles either. Don't use equal equal for strings. Don't use equal equal for doubles. And when we start talking about classes on Thursday, don't use equal equal for any of your classes, any of your objects created from your classes at all. You're only using equal equal for ints. Is that the end of the list? Yeah, just ints. You can use it for booleans, but if it's a boolean, you just assert true or assert false, whatever one you expect it to be. Or assert true. If you expect it to be false, you could even still use assert true and then not whatever your Boolean value is. You would just assert it directly. You wouldn't say assert true my Boolean value that I expect to be false equals false. You can do that, but it's a little much. Because you could just say assert true, not the value, or assert false is a method that you have access to as well. So really just don't use equal except for ints. There are other values like shorts and longs and stuff. We just don't use those in 116, so it's kind of irrelevant to us. Ints is the only one in 116 that you should be using equal for ever. Okay, and when we printed 0.1 times 3, you can do this in IntelliJ right now. You can do this in any language, really. Languages use the same representation for doubles. It's pretty consistently. If you do this in Python, you're going to get the same result. You're going to get 0.3, a whole mess of zeros, and then this trailing 4 way out here, which is not equal to 0.3. These are two different values. If you're asking for strict equality, the computer's going to look at this value, it's going to look at this value, and it's going to say, those ain't the same values. Now, to us humans, they're practically the same, but they are not identical. They're not identical, and you asked, are these two things identical? No, they're not. They're not identical. So the computer, rightfully so, is going to say, no, those aren't the same values, and your assert's going to fail. That's what it should do. That's what we want the computer to do. We want the computer to be 100% precise like that, even when it's a little bit annoying. So we have to do something about this, and let's talk about why this even happens first. And the reason, this is more of a 220 topic, but I got to dabble in it a little bit just to make my point here, is that a double is stored as a 64-bit value in the machine. 64 bits, 1 bit is a sign, 11 bits is the exponent, and 52 bits is, I thought that was called mantissa, but the fraction portion. So, and this is read as scientific notation. So this is your value, 52 bits for your actual value, and then that's stored in scientific notation in base 2. So it's 1 point this value raised to this power, or raised to 2 to this power, and then 1 bit for plus or minus if it's a negative value. So this is how doubles are represented in the device. Much more on that format in 220, as I just alluded to. That's as much as I need to say here. The big takeaway for now is that 64 bits, 64 is a finite number. It is not infinity. 64 bits. It doesn't matter if we have 32-bit. A float, at least historically speaking, floats, since it came up in chat a few times, we'll bring it up. Floats are 32-bit values. Same idea, but with only 32 bits. And then doubles are double the precision. They're up to 64 bits. That's where we get that name from. But back before every machine on Earth was a 64-bit device, and not every machine on Earth, but most of our devices are 64-bit devices. They used to be all 32-bit devices, so it made sense to have 32-bit values. But even before we had 64-bit processors, we started using doubles and having double the precision. And the same representation is used across languages, across architectures. It's a very standard format, standardized by IEEE. This is the format for a double. That's why even different languages, different operating systems, different hardware, if you multiply 0.1 by 3.0, the same format's used, everything is the same, and you're still going to get that trailing 4 at the end in a lot of languages. Some languages might truncate it when you print it to the screen, so you won't always see it, but in most cases, you're going to see that trailing 4. So why is this a problem? So doubles are represented with those fractions as sums of fractions of powers of 2. I assume you've seen some binary representation before in 191. Well, I don't know how safe of an assumption it is. Well, anyway, I'm going to go over it regardless. So, but with binary notation, it's just like decimal notation, where you have the ones digit, the tens digit, the hundreds digit, except it's powers of 2 instead of powers of 10. So we have the ones digit, the twos digit, the fours digits, the h digit, and then same thing on the other side. In decimal, we have the tens, the hundredths, the thousandths, the 10,000ths place. Those are all powers of 10. Same thing, but powers of 2 when it's binary. So we have the halves digit, the fourths digit, the eighths digit, the 16th digit, the 32nd digit, so on and so forth. So 0.11 in binary is read as 1/2 plus 1/4, which is 3/4. So this is how we would represent 3/4 in binary. Now in decimal, we know that there are some fractions that we cannot represent exactly in decimal form. For example, 1/3 is not the same as 0.333. No matter how many threes we write, it's 3 repeating out to infinity. So if we're trying to jam this in a finite amount of space, we have to truncate this at some place. So 1/3 is not equal to this. No matter how many threes we write, it's never going to be the exact value. Now, if that's the way we have to represent our values in the machine because it's using the 64-bit double IEEE representation, then we want to represent something like 0.1 or 1/10 in base 2. This would be fine in base 10. 0.1 in base 10 is just 0.1. Very easy to represent. In base 2, not so much. In base 2, 0.1 base 10 is 0.0001100110011 repeating forever, out to infinity. So at some point, we have to stop writing values, and that point is 52-ish bits in. The way this would actually be represented is it's always 1 point is assumed, and then this would be the first bit. So starting here and then go out 52 bits, that would be our fraction portion, and then our exponent would be 1, 2, 3, 4, minus 4. So this can't be represented exactly, and this has to be truncated, and this is what's going to cause what we call truncation errors, and that's why we're seeing that trailing 0.4. It's because 0.1 in base 10 cannot be represented in this double format that we use across all machines, devices, languages. 0.1 and many other values, of course, but 0.1 is just the one I like to use for example because it's the simplest one. 0.1 cannot be represented exactly in the machine. So a lot of times we're going to have doubles that are not exactly the values that we expect them to be, and that's where we get our issues. That's where our doubles get problems. So what do we do about this is we live with it. We just live with these truncation errors. That's just what we have to do. We're not can't really get rid of these. We not without extra tools. Like we're not gonna get rid of them with our vanilla doubles, with our regular doubles. So what we do is we live with them, and when we want to compare two doubles for equality, we don't actually check if they're equal to each other because that's going to let the truncation errors cause issues. What we do is allow for some tolerance. We allow for these truncation errors to exist and then still call the doubles equal in the end. And the way we do that is check if the doubles are within some small value of each other. So here I'm borrowing epsilon from math. Whenever there's a value that's expected to be very small, they call it epsilon. So I stole that from them, from the mathematicians, except I'm not going to use one character for my variable name. I'm not stealing that one ever. Epsilon equals 0.001. And what I'm going to do is check if the absolute value of the difference between the doubles is less than epsilon. If the absolute value between the difference of the doubles is less than this value, then these two values are within 0.001 of each other. And I'm going to say that's close enough for equality. That tolerance is going to eliminate any truncation errors. I shouldn't say any, but it's going to get rid of my truncation errors. But I want to make sure this value is small enough that it's not going to interfere with the logic of my comparison. So I'm going to allow some tolerance in my double comparison. Then I'm going to call my helper method here. This is an example of a method that doesn't have the test annotation because this method is not a test. This is a helper method. So I'm going to use this helper method to to make my tests more a little bit cleaner, cleaner to read, cleaner to write. And just because I use it here, I'll explain the epsilon. I did this so I could talk about it, but I kind of regret it because I don't feel like talking about it every semester. It's a little off the point. But I have a private variable, meaning this can only be read from within this class, so nobody outside this class can get my epsilon value because they don't need it. A final means it's a constant, and whenever meaning I can't reassign, I can never say epsilon equals something else later on. So it's a constant value. It'll always store the value 0.001. And whenever we have a constant in Java, the naming convention is to name it with all capital letters. So I have it all capital letters here because it's a constant. And then I can use that value in all of my methods, even though I'm only using it once here. Oops. I forgot I had a slide on that. And we want to choose a value for epsilon that is going to allow for truncation errors but not interfere with the logic of our code. For example, if I had this value at 10, which is way, way too high, if I had this value at 10, I can have two values that are 9.9 off from each other. And in most cases, I'm not going to want to accept that as the same doubles. If I have if I have 1.3 and 10, I don't want those being accepted as the same value, as effectively the same double, but that's what I'll get if I have this epsilon at 10. So I want to make sure this is small enough to not interfere, and for each application that might be slightly different. I like to start at 2 zeros as a starting point, and then if I decide that's too loose, I'll add a few more zeros and go tighter. But you don't want to go crazy with it. Once you add too many zeros, you're going to start having truncation errors cause issues again because you're effectively equal once you go out too far. So don't do too much. 2 zeros is usually good. I think that gets you through 116. But outside of 116, you need to think about what your value of epsilon should be and how tight you want your tolerances. For example, if it's distances on planet Earth, like distances between cities, you might want epsilon to be 1 kilometer or 1 mile. You might want that much variance, or even like 10. If the city is 10 kilometers wide, for example, if you're within 10 kilometers, you might want to accept that. But in most cases, you want this to be pretty small. And don't forget your absolute value. I see this in office hours at least once a semester. Don't forget your absolute value. If you're not taking absolute value, then the order of the arguments matters here. So if D1 is greater than D2, then there's no issue. You're going to get some really high value, which will do the comparison the way you want. But what happens when D1 is smaller than D2? So say D1 is 5 and D2 is 1 million. The difference is negative almost 1 million, which is definitely less than whatever you chose for epsilon. It's a negative value. It's going to be less than epsilon. But if you take the absolute value of this, now you're getting strictly the difference between these two values, regardless of which one is bigger than the other. It doesn't matter which order the arguments are. The absolute value of subtraction is always going to give you the same thing if you have the same two values in any order. And then your almost 1 million positive is definitely greater than 0.001. So we're correctly saying that those are not the same values. So don't forget your absolute value. I see that when students are cut and pasting this, especially when they don't write a helper method and they copy this line and paste it like 100 times for all their test cases. And somewhere along the way, they just pasted it wrong and they had zero thoughts in their head about what they were pasting. And they have an office hour visit. They're like, what the hell is going on here? And I lead them to finding out that, oh yeah, I forgot my absolute value. Because they weren't thinking at all about what they were pasting, just cut and pasting blindly. Never a good strategy. Just don't cut and paste blindly. But if you are, you're risking mistakes like that. It's always a silly mistake to make. Makes it clear that the student doesn't understand why they're cut and pasting it. They just know they saw it in lecture and that they need to have it, or else AutoLab gets mad. And then they forget. Usually, students will get it on task 1 because we just covered it in lecture. But once it gets to like task 6, they forget and they just know that they have to cut and paste this thing everywhere, and it gets weird, gets awkward. For a line like this, does the 0.001 represent the margin for error? Yes. So we're saying what in English, what this is saying is are D1 and D2 within 0.001 of each other? So is the difference between them less than this tolerance or this margin of error? If it is, then pass this test case. And by the way, you can have asserts in your helper methods like this. And I do recommend it when we get to test 2 and onward and I have the testing utility methods. I do recommend having your asserts right in the utility methods themselves. Though I don't require that. I think I will start in the fall, start requiring that. But the, are these within 0.001 of each other? Okay. Or you take all that, everything we just talked about, and stuff it into an assert equals. If you use assert equals, you won't have that issue that forgetting your absolute value that I just talked about. Assert equals does work with doubles, but you must give it a third argument. The third argument is your epsilon. That's your tolerance. That's your margin for error. That's your allowance. I forget what the library calls it. I think they call it tolerance. I forget. But this is going to say ry and 0.3 within 0.001 of each other. And again, I have my inputs backwards. This should be 0.3, then y, then the tolerance. Minor difference. It just changes the feedback that assert equals will give you if the test fails. But I do like to have them the right way, and I missed it in all these slides. TLDR, never use equal to compare doubles. You always want to allow some tolerance because we have truncation errors. Very, very, very important. That'll be true throughout your whole career, or else you're going to have really, really wacky bugs that are hard to debug. Don't put yourself in that position where you're spending hours of your life or even days trying to debug one of these issues because you used equal to compare two doubles. Never, ever do that. Okay, we're cooking. One more. We're pretty far behind on the clock, but I think I can get through this one fairly quickly. Most of these slides is a big old memory diagram, which I can rip through pretty quickly. Let's make sure we do exactly that. First, interpretation versus compilation. This is a one-off topic where I put in this lecture because usually I have some extra time in this lecture to talk about it. I just want to talk about this very briefly. Interpretation, when you run a program, when you run a computer program that, mostly when that you wrote in this context, you write a computer program. If that program is interpreted, that means that your code is being executed one statement at a time. It executes line 1, then line 2, then line 3, and just goes through your code and runs your code directly. Versus compilation, where before any of your code is ran, your entire program is translated into another program in another language, usually another language, and then that translated code is interpreted by an interpreter. That code is ran line by line. When you have a compiled language, when your code is compiled, your code that you wrote is never actually executed. It's compiled into another language, and then that language is executed through an interpreter. So this is a difference between interpretation and compilation. Python, JavaScript, a bunch of others, but Python is the one you would use. Python was interpreted. That was an interpreted language. Python's converted into machine code by the interpreter. So everything has to be converted into machine code at some point. But in Python, it's converted by the interpreter itself. In Java, I'll get to the next slide and talk about Java. Java's a little weird. But with Python, the interpreter is going to turn into machine code because the only thing your CPU can understand is machine code. If you have an Intel processor, it has the Intel instruction set. That's the only thing your processor can actually do. So everything has to be compiled down, or not compiled, has to be converted in one way or another, either interpreted or compiled, down to machine code at some point. Python that happens with the interpreter, and it's one line at a time, which means and when you have errors, if you have any errors, they're more commonly to be runtime errors. Your program's going to it'll run some lines of code, but then when it gets to a line of code with an error, the interpreter won't know what to do with that line of code, and then it'll crash. Your program blows up. But one of the trade-offs with this is your program runs immediately. When you're running your Python programs, you click the go button and it goes. It just books right away. Compare that to compiled languages, which for our purposes includes Java. That's our big one. It will also include C, which you'll see in 220. CSE116 is all in C. So you're entering the world of compilation starting in 116. You'll be in compiled languages for a while. 2 semesters at least. Java is a compiled language, meaning that it's converted into another program, meaning the compiler will go through all of your code, every line of code, and translate it into another language before your code is ever executed. So this is why when you hit the go button in IntelliJ when you're running a Java program, you hit the go button and it just kind of sits there and it thinks for a while, and it thinks and it thinks, and you got a progress bar in the bottom of your screen and you're like, what is taking so long? That's the compilation process. And then after it's compiled, it'll execute, and more often than not, the compiled language is going to execute faster than the interpreted language because the compiler can add a lot of efficiencies in as it's doing the translation. It's going to run faster, but it takes longer to do that compilation process. But in Java, if you have your Java program, you write some code and you run it, you'll see that it'll go slow when you run it. But if you immediately run it again, it's going to go fast because it doesn't have to recompile. It already compiled. And IntelliJ will know that you didn't make any changes. It'll just run the old compiled code. So here, if you have errors, they're more likely to be compiler errors. What this means is when the compiler is going through all of your code, it's doing a lot of checks to make sure that your code is legit. If it comes across any errors, it's not going to run your code at all. It's going to say, hey, during compilation, I ran into this issue. You might want to fix this because I'm not running your code. I can't translate your code until you fix this issue. This is why Java can be strongly typed, because we have the compiler which is enforcing that typing. Python being interpreted can't enforce any typing because when it's running a line of code, it doesn't know what the next line of code even is or does or anything about it. Java does because it's compiled. So that's why we have a lot different feel for this language. It's because it's a compiled language and not an interpreted language. Java is compiled down to Java bytecode, not machine code. Everything has to be machine code eventually. It's going to be compiled to Java bytecode, which is ran by the Java Virtual Machine, the JVM, or usually just called Java. And then the JVM interprets the Java bytecode, converts that to machine code, and then actually runs the code. So the Java bytecode is interpreted. Java itself isn't compiled into Java bytecode. And this, whenever you see these pop-ups, Java has an update, which I feel like it's less intrusive these days, but this used to be a fact of life that every time you touched any machine, it'd be like, you have to update your Java. That's the JVM. That's the JVM running on your machine. The JVM runs on billions of devices. They'll constantly remind us. This is already installed on probably every device that you have, most likely, including a lot of embedded devices too. Java runs anywhere, practically anywhere. So your code, you can compile the Java bytecode and run it on any device that has Java installed on it, the JVM installed on it. So this makes Java very portable. You don't have to compile for Windows and Mac separately like you'll have to do for C. Well, you won't have to in 220. You won't have to worry about deployments. But in Java, you don't have to worry about that at all. You compile it once. That Java bytecode is completely portable to any device running Java. One of the really huge selling points when Java first came out, because it was the only language that was so versatile like that. Very handy feature to have. Okay, so let's talk about recursion. which is kind of a shift of gears from testing, but recursion's another one of them topics where I don't know, like I need to introduce it somewhere before we start using it. We'll start using it in linked lists, but I want to give some introduction to recursion before we get to linked lists, or else we're jamming way too much in the linked list week. Okay, so recursion is when a method calls itself. Recursion itself can apply to functions. Since we're in Java in 116, we only have methods, so I'm going to say methods. But it, of course, also applies to functions that call themselves. But it's when a method calls itself, that's recursion. That is the definition. That's it. That's the whole definition. Recursive method is a method that calls itself, period. That's it. Anything else isn't really recursion, and if you have this, it definitely is recursion. It's a method that calls itself. That's it. You know recursion now. It's like I wave a magic wand. You know recursion now. Recursion, I'll give my preface to recursion. Recursion's a very slippery topic that it's hard to get a grasp on how recursion works when you first learn it. It's one of them topics that just doesn't make sense, and then it doesn't make sense, and then it doesn't make sense, then it still doesn't make sense, and then all of a sudden it clicks and it's like, holy crap, I understand recursion. So it can take a long time for that click to happen. For me, it didn't happen until I was taking 331. Like it can take years for it to really click on what recursion is really doing. So by the end of 116, I don't necessarily expect you to fully grasp recursion, but I do expect you to be able to write a few recursive methods. Specifically when we get to trees, that's where that's the first time you really have to use recursion. I'll recommend that you use recursion for linked lists. But for now, let's just introduce what the hell recursion is and go through one memory diagram. This is a recursive method. We're defining a method. It's called add. Its goal is to add two numbers. And this is one of them kind of awkwardly written methods where I'm saying we would want some good unit testing for a method like this, because some smartass dev is going to write this implementation instead of just saying return A plus B. They're going to write some garbage like this, which is garbage. You should never write an add method like this. I'm only doing this to force a recursive example with an application that we all know what the expected output is. Somebody's going to write it like this, and you're going to want to rely on your unit testing to make sure that they didn't do anything stupid, that this does actually work. Does it work on 0? Does it work for positive values? Does it work for negative values? It has to work on all those values. Like a loop within a loop, it kind of takes a loop and flattens it out into one method call, but each time it calls itself, that's similar to an iteration of a loop. And usually you can rewrite your recursive methods as loops, but not always. We'll see, specifically when we get to trees, we'll see where we wouldn't be able to rewrite our recursive methods with loops. But recursion and loops, you can see those as two solutions to the same problem. We want to repeat an action some variable number of times, some number of times that it's not predetermined before the code executes, kind of solving the same problem. So we're defining a method named add, and we're calling a method named add. We have a method named add that calls a method named add, and these are, in fact, the same methods. This is a method that calls itself. That means this is a recursive method. This is what recursion is. It calls itself, so it's recursive. So how does a method that calls itself actually work? Like this should be mind-boggling the first time you see it. If this is the first time you're seeing this is absolutely insane. This is friggin' nuts that a method that we're writing, we didn't even finish writing the method. So when I'm typing this up, like I'm not even done writing the method yet, and I get to this line and I'm like, this method that doesn't even have a closing brace yet, I'm gonna freaking call it. I'm gonna call this method that's not even done yet. It's gonna call itself, so its definition depends on its own definition. This is something we learned, back in grade school, that you can't define a word using the word itself, but that's exactly what we're doing with recursion. We're defining a method using the method itself. That doesn't make sense. So let's see this in a memory diagram. And I think this is the easiest way to see exactly how this works is just visualizing what happens in memory. This is the easiest way to see how a recursive method works. And by the way, when I say understanding recursion, I mean getting to the point where you can confidently write recursive methods that don't exist yet. You should be able to trace through recursive methods right now. Like I shouldn't even have to really say anything about it. You should be able to trace them and be able to follow the logic of how they work. But to be able to write a recursive method is a whole nother level of understanding. A whole nother I like the way I said it. A whole nother level. So let's see this in a memory diagram so we can see how this unfolds. We have our call of add 3, 4. That's a method call. It returns to result. A and B, add, everything the way we've done every method call since 115. A is 4, B is 3. B is not 0. B is greater than 1. This else is here in case B is negative. So we're not actually going to see that in this example. But that's there just for completeness. In case B was negative, we want to be able to handle negative values. So we're going to make a recursive call. Add is going to call itself. And here's the trick with recursive methods when you're doing your memory diagrams. When you get to this method call, there is no trick. There's no trick at all. It's just a method call. You go in completely blind and you just turn your brain off and you say, oh, a method call. Method named add. Where's the method named add? Oh, here it is. And you call that method. That's it. That's all there is to it. And then as we go through this, we're going to start seeing how the magic happens. But we're just blindly, okay, add, throw that on the stack. New method call, new stack frame, it's still add, throw it on the stack. And I'll say right now, with recursive methods, I don't care where you put your return arrows. There's no mechanism in the tracing tool to have a return arrow point to a previous stack frame. So if you don't have your return arrows or your return arrows point to the original value, I don't care. Unless I set up like int x equals add of this and then return x, then your return arrow would go to x in the previous stack frame. If I do something like that where there's a clear answer, fine. Even then, return arrows, I'm never going to fail you for missing your return arrows anyway. So, I mean, get them right, please, but it's never going to cause an F in the class. Okay, so we just put our stack frame on the stack. Add of a plus 1. This, when we're evaluating these arguments, we were in this stack frame. So we have to pay attention to what stack frame we're in when each expression is resolved. A plus 1, A is 4, so A plus 1 is going to get 5. B minus 1, 3 minus 1 is 2. So that's what's passed to the next stack frame. A and B are 5 and 2. Now we have another stack frame. We have the main stack frame. We have the first recursive stack frame, the second recursive stack frame. And we're going to just start over in this stack frame. This stack frame, it's just like any other method call. If B equals 0, that's false. If B greater than 0, that's true. We get to this line, and we do the same thing. We just do it over again. Add of A plus 1, that's 6. B minus 1 is 1. So we put another frame on the stack with 6 and 1. Is B equal to 0? No. Is B equal to 0? No. Is B greater than 1? Yes. So we put another frame on the stack. A plus 1 is 7. B minus 1 is 0. Another frame on the stack. And we have 5 stack frames, including our main stack frame, on the stack right now. And I have these arrows to indicate where each stack frame is. Each time a stack frame gets its return value, we have to remember where it was, so we remember what it was doing. It can pick up its execution and resume, just like any other method call, but we have a lot more method calls on the stack now. With this method call, with this stack frame, is B equal to 0? That's going to be true now, and this is where we're going to hit what we call our base case of our recursion. This is any situation, any call of a recursive method that doesn't call itself. And this is extremely important. This is how we stop the insanity. This is where things stop, is when we hit a base case. We hit our base case of b equals 0 and just return a. So now, instead of making another recursive call and continuously putting frames on the stack, instead we return and cap off the recursion, return 7 back to this stack frame, and this stack frame returns the method ended. It pops off the stack, and control goes back to the previous stack frame on the stack, the new top of the stack. This is the stack frame that regains control. So the stack frame says, oh, hey, I got control back. I was waiting right here for this method call of add to return. It did return. It resolved to the value 7. So I'm going to continue execution where I left off. This resolved to 7, and I'm just returning that. So I'm going to return 7 back to this stack frame. So this stack frame gets 7, and all it's going to do is return it. Return 7 back to this stack frame. This stack frame says, hey, I'm the top of the stack again. All right. Where was I? Where did I leave off? It left off right here. This resolved to 7. It's going to return 7 back to this stack frame. This stack frame gets control again. It's now the top of the stack again. It picks up where it left off right here. It was waiting for a return value. It gets the return value 7. It returns 7 back to the main stack frame. It picks up where it left off. It was waiting on this method call to resolve. It resolved to 7, which is 4 plus 3, so things are checking out there. This resolves to 7. It says, okay, let me pick up there. I get 7. I was assigning that to result. Result gets 7. Print result to the screen. End of program. So that's and this is what it looks like in the tracing tool. We have our main stack frame with just result, and I didn't do any return arrows for my recursive methods except the first one to say that returns to result. And then my A and B, all that's the same all the way down. And then don't forget to cross out the stack frames and print 7. So this is recursion. So nowhere in there was there like some mystery of what happens when a method is defined by itself, by its own call. We trace through it just like any other trace. Just pretend that this is a method call just like any other method call. It just happens to call the same method. But when we trace through a recursive method, there really is no trick. It just kind of worked out. And the reason it works out is because we have all these stack frames that are waiting for the next recursive call to return. Eventually, we're going to get to the base case. When we get to the base case, then we start returning, and then we return all the way back up the recursion to finish the process. So all these methods were dependent on itself till it was dependent on itself with a fully defined method. Like we have the recursive case here, 2 recursive cases in this instance, and the base case here. We're going to keep making recursive calls till we hit the base case, and then we start returning and finishing. Because once we hit the base case, it starts the collapsing of these recursive calls. And again, I think that makes so much more sense through a memory diagram. One of the huge advantages to having memory diagrams as part of the course is recursion makes a lot more sense when you can see it completely unfold and then roll back up. Hey, with 1 minute to spare. Look at us. Alright, so I'm going to take end this lecture. We'll do the next lecture, and then office hours. I think I forgot to mention office hours last time. I'll have office hours after the second lecture. I'll be busy until then. 2 to 3 is my office hours. So I'll be there in the Zoom meeting after that. Yeah, exactly. It's like setting up dominoes and knocking them down. I like that analogy. All right. So programming test 1, Get that done. You should have that done by the next lecture. That's the expectation. So you'll have it done before the next lecture starts. So get on that. If you're running into troubles, come to office hours. We'll be there to help you. Gerline should be adding more office hours. She was out of the country for a while. I forget exactly what her situation is, but she'll update to get some more Tuesday, Wednesday office hours because we're a little light on Tuesday, Wednesday right now. We got pretty good on Thursday, Friday. That's probably what Thursday, Friday is going to end up looking like, is this. But Tuesday, Wednesday's we need a few more office hours there. All right. Take care, everyone. I'll see you on Thursday after you've done programming task 1. Take care, everyone.